So, this is the last lecture on linear algebra. As we have already seen, linear algebra has lot of application in linear models. Indeed, we can say that understanding linear algebra is the most important aspect of linear models. In this lecture, we are going to take a look at some rather advanced concepts of linear algebra. These are not very frequently used to linear models, but it is important to understand them in order to carry forward with this topic. Eigenvalues. Let A be a square matrix of order n and lambda be scalar. Let lambda 1, lambda 2 lambda n be the roots of the characteristic equation, which is determinant of A minus lambda I equal to 0 of A. Then lambda 1 to lambda n are called the eigenvalues of A. Note that determinant of A minus lambda j I equal to 0 for all j, that is, the columns of A minus lambda j I are linearly dependent, implies A minus lambda j I times x j equal to the 0 vector for some non-zero vector x j. X j may be complex, and that implies A x j is equal to lambda j x j. Eigenvectors. The non-zero vector x j such that A x j equal to lambda j x j is called the eigenvectors of A corresponding to the eigenvalue lambda j. Characteristic roots. Find values of a scalar lambda for which there exist vectors x not equal to 0 satisfying A x equal to lambda x, where A is a given nth order matrix. The values of lambda that solve the equation are called the characteristic root or eigenvalues of the matrix A. Spectral decomposition. Let A be a real symmetric matrix of order n, then there exists an orthogonal matrix P such that A equal to P lambda P transpose. In other words, A equal to summation I from 1 to n lambda I Pi Pi transpose, where P equal to P1 to Pn and lambda equal to the diagonal matrix with entries lambda 1 to lambda n. And here the lambda 1 to lambda n are the eigenvalues of A. The matrix P is made of the orthogonal eigenvectors of A. Quadratic forms. Let A be a square matrix of order n. For any vector x and y, we call x transpose A y as a linear form. We call x transpose A x for any x not equal to 0 as quadratic forms. Here, as a quick note, let me add that x transpose A y is more commonly referred to as a bilinear form because it is linear in both x as well as y. X transpose A x is double summation A I j x I x j, where A equal to A I j and x transpose is x 1 to x n. Properties of quadratic forms. 1. A is NND if and only if all the eigenvalues of A are non-negative, that is lambda I greater than equal to 0 for all I. 2. A is positive definite or PD if and only if all the eigenvalues of A are positive, strictly positive, not just greater than or equal to 0 as written. 3. A is positive definite if and only if all its principal leading minors have positive determinants. 4. All PD matrices are non-singular. However, converse is not true. That is, a non-singular matrix need not be PD. 5. Supremum of X transpose AX divided by X transpose X, where the supremum is taken over all non-zero vectors X, equals lambda 1, and similarly the infimum taken over the same set equals lambda n for any symmetric matrix A, where lambda 1 is the smallest eigenvalue and lambda n is the largest eigenvalue of A. Here we are working with a real symmetric matrix A. So, lambda 1 to lambda n are all real numbers and hence may be ordered. Cholesky decomposition. Let A be a positive definite assumed to be symmetric matrix, then there exists a lower triangular matrix Xi with positive diagonal entries such that A equals Xi Xi transpose. Inverse of a matrix. A square matrix B is said to be an inverse of a square matrix A if AB equal to BA equal to identity. It is denoted by B equal to A inverse. A inverse exists if and only if A is non-singular. If A inverse equals A inverse A equals IN, then A inverse is the inverse of A. If both A inverse and B inverse exist, then C of A whole inverse equal to 1 by C A inverse, C being a non-zero scalar. 2. AB whole inverse equals B inverse A inverse, and determinant of A inverse is 1 over determinant of A. 4. If 1 plus B transpose A inverse A is not equal to 0, then A plus AB prime whole inverse equal to A inverse minus A inverse A B inverse A inverse divided by 1 plus B transpose A inverse A. Vector spaces. Suppose E is a subset of Rn, the n-dimensional space. If X is in E, Y is in E, and A, B are scalars, then E is called a vector space if Ax plus By belongs to E. Euclidean n space, the set of all vectors in Rn, forms a vector space called the Euclidean n space. Length of a vector X is defined by the given formula, which is its distance from X to 0. Gram-Schmidt orthogonalization. Given a set of independent vectors, we can construct a set of orthogonal vectors such that the spans remain the same. Orthogonal projection of a vector. Let V be a subspace of Rn and alpha not belonging to V. Then there exist two vectors beta and gamma such that alpha equal to beta plus gamma. Beta in V and gamma not equal to 0 is a vector orthogonal to V, and B and gamma are unique. If we remove the condition gamma not equal to 0, then the result holds even for alpha belonging to V. Rank of a matrix. The rank of an m by n matrix A is the maximum number of linearly independent rows or columns of A. We write the rank using the notation rank first bracket A. Properties of rank. 1, 0 less than or equal to rank of A less than or equal to minimum of m and n. 2. Rank of a matrix equals the rank of its transpose. Rank of A plus B is less than or equal to rank of A plus rank of B. Rank of AB is less than or equal to minimum of rank of A and rank of B. For any non-singular matrices C and D, rank of CAD equals rank of A. For A, rank of A equal to n if and only if A is non-singular. If A is diagonal AI, then rank of A is number of AI not equal to 0. A matrix A is said to have full column rank if rank of A equals n and full row rank if rank of A equals m. A square matrix A is said to have full rank if rank of A equals n. In that case, A inverse exists and we say A is a non-singular matrix. Elementary operations: permutation of two rows or columns, multiplication of a row by a non-zero scalar, addition of one row to another. We shall denote these operations respectively by P, M and A. Theorem: diagonal reduction of a matrix. Let A be M cross n matrix of rank R. Then we can construct a non-singular square matrix B and C of orders m by m and n by n respectively using elementary operations such that BAC becomes the matrix shown in the right. Rank factorization: let A be a matrix of rank. Then we can write A equal to PQ, where P is a full column rank and Q is a full row rank matrix. Generalized inverse: a matrix G is said to be a G inverse of A if x equal to GY is a solution for AX equal to Y whenever the system is consistent. Theorem: G is a G inverse of A if and only if AGA equals A. Proof: consider a system of equations AX equal to Y and that Y belongs to mu A. That is, the system is consistent. Suppose G is a G inverse of A, then x equal to GY is a solution to AX equal to Y. That is, A times GY equals G, AG times AX equal to AX, that is AGA is equal to A. Alternatively, consider the system of equations AX equal to AJ, the jth column of A. These are consistent systems since AJ's belong to mu of A. If G is a G inverse of A, then by definition x equal to GAJ is a solution to AX equal to AJ. Hence, we get AGA equal to A. Conversely, suppose AGA is equal to J, then AGAX is equal to AX, and after a few steps which are given in the slides, we see that we can write G inverse of A as A minus. Thus, AA minus A equal to A. Notes: rank of A is less than or equal to rank of G. 2. Every matrix A has a G inverse. 3. G inverse is not unique in general because the matrices B and C in diagonal reduction are not unique. 4. If A is non-singular, then G is equal to A inverse is unique. Idempotent matrices. A square matrix A is said to be idempotent if A square equal to A. Examples: I 1 by n j, PA equal to P A prime A whole inverse A prime, etc. Notes: if A is idempotent, then so is I minus A. If A is idempotent, then rank equals trace. If A is non-singular and idempotent, then A has to be the identity matrix. If A is idempotent, then rank of A plus rank of I minus A must add up to the size of the matrix. Notes: every symmetric matrix A also has symmetric G inverse. Proof: suppose G1 is a G inverse of a symmetric matrix A, then what we do is we just work with G1 transpose, which is also shown to be a G inverse of A. define G equal to the average of G1 and G1 transpose, then G also satisfies the condition AGA equals A. Thus, G is a G inverse of A, and by construction G is symmetric. Theorem: let A be a given matrix and G be a particular G inverse of A. Suppose Y belongs to mu A, then the class of all solutions of Ax equal to Y is given by I equal to set of all x that can be written as Gy plus I minus Ga Z, where Z ranges through Rn. Proof: let x be equal to Gy plus I minus Ga Z, then Ax equal to A times x. After some manipulation, this becomes Ag plus 0. Therefore, Ax equal to y, which means x equal to Gy is indeed a solution. Next, we need to show that every solution can be written in the above form. Let x naught be any solution. Then x naught equal to Gy plus x naught minus Gy, that is Gy plus x naught minus G A x naught, that is G of y plus I minus G A x naught. Take z equal to x naught, hence x naught belongs to L. Theorem: if rank of A equals R, then the maximum number of linearly independent vectors in L is n minus R plus 1. Proof: consider mu of I minus Ga, which is x into I minus Ga Z for all z in Rn. Since rank of I minus Ga is n minus R, there are as many linearly independent vectors in the space that form the basis of this space. Let I minus Ga Zi be a basis for mu of I minus Ga. Let x naught be Gy and xi be defined as given. Then claim is the set is linearly independent. Consider the sum to be equal to 0. Split this sum into two sums as shown, multiply by A to get the first sum equal to 0. So, the second sum is equal to 0. So, the third sum is also equal to 0. Ci equal to 0 for all I, since I minus Gs Zi are the basis linearly independent vectors. Thus, we have all the Ci is equal to 0. Therefore, their sum is equal to 0. Therefore, C0 is equal to 0. Therefore, xi's are linearly independent. Since every x in I can be expressed as linear combination of xi's, hence the maximum number of linear vectors in n minus r plus 1. Reflexive G inverse. A G inverse G of A is said to be reflexive if AGA equal to A and GAG equal to G. Moore-Penrose inverse denoted by A plus. Suppose there is a matrix A plus such that A plus is a reflexive G inverse and AA plus and A plus A both are symmetric. Such a matrix A plus is called Moore-Penrose inverse of A and it is unique. This module reviewed some of the more advanced topics of linear algebra. These are not essential for understanding the basics of linear models, but whatever we have learned in this module will prove important if you want to further continue your study of linear models. Thank you.